right, so in the last section, we looked at, last couple sections rather, we've looked at mean and standard deviation. Again, the mean being a measure of center, a good representative for certain sets of data. And then that standard deviation, essentially quantifying the variability within the data set. How different are the individual values from the mean? What we want to look to now is actually starting to use the mean and standard deviation and see what kind of information we can gather from those. So let's go ahead and get started here. And we are going to start with these measures of relative standing. So what do I mean by that? Well, let's start with this question. What does standard deviation tell us? We've seen already how standard deviation describes the variability, but you might think of it this way. It really tells us how spread out our data is, how spread out our data is, okay? And when we say spread out, again, we were referring to spread out from the mean. And one of the wonderful things we have is this empirical rule. We've talked about normally distributed populations. We looked at histograms that were normally distributed, and we said that's that nice bell curve. Well, the empirical rule gives us some wonderful information when the data is normally distributed. And again, this is a big assumption, right? We have to have this condition. But if we do, then the following is true. About 68% of the values lie within one standard deviation of the mean. 95% within two standard deviations, and 99.7% within three standard deviations of the mean. So you can kind of see how the standard deviation gives us something to count by as we move out from the mean. And the more and more we move out, the more and more values we capture. So if this is the mean here, then from one standard deviation on either side, so this would be the mean minus sigma. This would be the mean, oh, I'm sorry. This would be the mean plus sigma. We've got 68%. And when we move two standard deviations away, so mu minus 2 sigma, mu plus 2 sigma, we've got 95%. And then by the time we move out 3 standard deviations, so again, that coefficient of sigma, right, that's the number of standard deviations I moved out. By the time we get out here, we've got a whopping 99.7% of our values. And you can kind of see the area, right? As you move out 3 standard deviations from the mean, look how much of the area in here you've gathered and you captured. And this is actually somewhat scrunched. I mean, 3 standard deviations typically is even farther out. These tails are somewhat enlarged. When you have, when you're within 3 standard deviations of the mean, you've accounted for nearly all of the values. So this is known as the empirical rule. Very, very valuable result. And it also lets us describe in an objective way what we mean by unusual. So if I were to use the word unusual, you know, out on the street somewhere, someone might say, oh, well, that's just your opinion. Well, in statistics, we've agreed as a discipline what we're going to call unusual. And we would say that that's any value beyond 2 standard deviations. So coming back to this, it would be any value that's outside that 95%, okay? So any value outside that 95% or 2 standard deviations, we are going to call unusual. If it's beyond 2 standard deviations above, we would say it's unusually high. And 2 standard deviations below, we would say unusually low. So let's see how this works with this example. You've got runs in a baseball game. The mean runs scored in a game is 10 with a standard deviation of 2.4. Would it be unusual to see a game with 15 runs scored? How about 6 runs scored? Well, let's start with what would be unusually high. Well, unusually high is going to be the mean plus 2 standard deviations. So if the mean is 10 and the standard deviation is 2.4, then 10 plus 2 times 2.4 is going to give me what, 14.8? And then unusually low, well, now I'm going to look at 2 standard deviations below the mean. So if we've got mu minus 2 sigma, we are now going to compute, what is that? 10 minus 2 times 2.4. And that's going to be 5.2. And so if you think about a number line here, you've got 5.2 down here, you've got 14.8 up here, and anything out here or down here is going to be unusual. So would it be unusual to see a game with 15 runs? Well, yeah, because 15 sits out here somewhere. But notice that 6 runs is in there. It's between 5.2 and 14.8. So 15 runs would be unusual because it's beyond 2 standard deviations from the mean. Whereas 6 runs, of course, would not. So you see how that works. We're essentially finding what value corresponds to those 2 standard deviations above and below and deciding if the values we're given are within the appropriate interval. Now, what happens when data isn't normally distributed? Because that's a big assumption, and it's not always the case that data is. And if that's the case, then we have Chebyshevs Rule, named after the Russian Chebyshev. And so this is a weaker statement, but it still has some power. For any distribution, not necessarily normal, again, for any distribution, the fraction of data line within k standard deviations of the mean is, notice, at least, not equals, but is at least 1 minus 1 over k squared. So let's take a look at how Chebyshevs will work. A recent survey found that the average time a teenager spends on the internet each day is 4 hours. The standard deviation is 0.5 hours. What percent of teenagers spend between 2.5 and 5.5 hours online each day? Well, we need to first notice that we cannot assume normality, right? There's no indication here that the times spent online are normally distributed. So if we can't assume normality, then we're going to use Chebyshev. By the way, I believe this is 1.7.2, not 6. All right, that means we need k. So if you look at the 2 values we have, 2.5 and 5.5, each of those are a certain number of standard deviations away from the mean. The question is, how many? So if you take the mean and subtract a certain number of standard deviations, so the standard deviation, whoops, is 0.5. So 4 minus how many 0.5s is going to give me 2.5. Well, if you solve this, little algebra here, you'll get subtract 4 from both sides. You're going to get k equals 3. And we can play the same game on top. So 4, the mean, plus a certain number of 0.5s, so 0.5k, is going to get me to 5.5. Well, if you solve this, you again get a k of 3. So k is equal to 3. And so I can now compute 1 minus 1 over k squared. And so that's going to be 1 minus 1/9, which gives us really just repeating 8s. And so we might make a statement like this. At least, and I'm going to round down here just to be accurate, but at least 88.8% of teenagers spend between 2.5 and 5.5 hours online each day. Okay, so again, we didn't have the normality assumption. We used Chebyshev. We found what k was, how many standard deviations those data values are from the mean, and that let us come up with this percentage. Okay. Well, what about standardizing data? Right, we've looked at the normal distribution here, the empirical rule, but what if we have this situation? Let's say you get an 82% on your statistics midterm. The mean on this midterm was 70% with a standard deviation of 5.6%. Meanwhile, you have a friend in another class, they get a 91%. She gets a 91% on her midterm. That mean was 88% and a standard deviation of 4%. Both exam scores are normally distributed. That's great. We need to know that those sets of scores are, so we can use empirical rule. Who should be more proud of their midterm grade? Now, what do I mean by more proud? I'm essentially saying who scored relatively higher. I mean, you got an 82%. That is just absolutely true that it's less than 91%. Your friend got an A, you got a B. But what's also true? What's also true is that the average on your test was a C, 70%, barely a C, and a standard deviation of more than half a grade, 5.6%. Whereas there was a high mean on your friend's test, and that standard deviation was less than half a grade, 4%, right? So taking all that information into account, who did relatively better? Well, we essentially need to standardize the data, and we do that using what's called a Z-score. So let's talk about Z-scores. Here's the formula. You might also see it this way, just depending on what we're given, right? It's not very realistic that we know the population mean and standard deviation, but either way, and that does something for us. And I want to kind of explore what that actually does for us. So a Z-score is X minus the mean, that difference divided by the standard deviation. Now think about what this is. It's a ratio, right? And so you're essentially saying how many standard deviations fit into that difference. Let's think about what this is telling us. So we're going to describe each of these Z-scores, and I'm hoping that you discover a pattern here and can make some meaningful observation. So remember that we have Z equals X minus mu over sigma. If X is equal to the mean, so if X is actually the mean, and again, it could be mu or X bar, depending on what we're dealing with here. X bar might be all we have. A lot of times it will be. Then what happens here? Well, I'm going to replace that X with mu. And so I get mean minus mean over standard deviation. Well, that's 0 over standard deviation, which is 0. When X is the mean, the Z-score is 0. By the way, if X is the mean, how far away from the mean is it? I'll ask that again. If X is the mean, how far away from the mean is it? Oh, 0. What about this one? a value that is one standard deviation above the mean. So again, we have x minus mu over sigma, and we are saying that the value of x, this x, is one standard deviation above the mean. So we take the mean and add one standard deviation. All right, well, what does that do to this formula? Well, x is now mu plus one standard deviation. Again, this piece right here, right, that's x. And that's all over sigma. Well, what do you notice? The mu's, right, are gone. Mu minus mu is 0. And you got 1 sigma over sigma. And yeah, you might not write 1 sigma, but I'm trying to bring up a point here. Notice mu, or z rather, is 1. When x was 1 standard deviation above the mean, z is 1. What if the value is 2.37 standard deviations below the mean? Well, again, go to our formula. And now we're saying that x is the mean minus 2.37 standard deviations. All right, well, let's see what happens. That's going to give us a z of mu minus 2.37 sigma minus mu all over sigma. Again, this piece right here is my x. Well, mu minus mu is 0. So you have negative 2.37 sigma over sigma. The sigmas cancel and you've got negative 2.37. So in other words, when the value is 2.37 standard deviations below the mean, our z-score was a negative 2.37. You should start to see something here jumping out at you. So what does a z-score actually tell us? Well, it tells us how many standard deviations above or below the mean a particular value is. That's what it tells us. If z is positive, then the value is above the mean. If z is negative, the value is below the mean. Now, keeping this statement in mind, you might back up a little bit and revisit what we just looked at and verify that that's true. I told you how many standard deviations from the mean any of those x's were, and that's exactly what we got for our z-scores. So a z-score tells us how many standard deviations above or below the mean a particular value is. And so let's describe or find this indicated score, a value that is unusually high. Well, unusually high means that the value has to be has to be greater than the mean plus 2 standard deviations. Well, that means any value that's unusually high is going to have a z-score greater than 2. Because again, what does a z-score tell us? How many standard deviations from the mean you are. So unusually high, it's got to be 2 away. That's the unusual part. And high, meaning above. So positive 2. How about unusually low? Well, in this case, x is going to need to be less or below the mean minus 2 standard deviations. Well, that's going to give us a z-score less than negative 2. And so in terms of z's, right, if these are z's and zeros in the middle, here's 2, here's negative 2. Anything out here or down here will be unusual. okay? So just like 2 standard deviations, whatever value that is kind of the magic number for determining if a value is unusual. If we're talking z-scores, that magic number becomes 2 or -2. All right, what does that do to our standard normal distribution? Well, if you think back to what we had before, this was the mean, and then the mean plus 1 standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations, and similarly as you move to the left. But if we talk about z-scores, well, the mean is just 0. 1 standard deviation above is 1. 1 below is -1. 2 above, 2 below, 3 above, and 3 below. That's it. The same percentages are in play. You still have 68% within 1 standard deviation, and you still got about 95% within 2 standard deviations. And if you remember what we said about 3 standard deviations, you still got about 99.7% within 3 standard deviations. But gosh, look how nice that scale is. Right? You're just talking about whole numbers. And notice that's also decontextualized, right? We've standardized the data. It's independent of the context, whether we're talking about red blood cell count or heights or weights or whatever, but this is just decontextualized data. It's standardized. So let's look at this motivation problem again. We've got 82% was the mean, your mean. I'm sorry, was your score. The mean was 70%, and the standard deviation was 5.6%. You have your friend, on her exam, she got a 91. The mean was 88, standard deviation 4. So who should be more proud? Well, let's take a look. So let's take a look now and kind of see what we got here. We've got, let's see. So for your exam, you need to compute the z-score, right? If I can compare the z-scores, if I can figure out who was more standard deviations above their class's mean, then we'll know who did relatively better. So for your exam, well, you had a score of 82. The mean was 70. The standard deviation was 5.6. And so if you compute that, let's see what we get. Let's see here. Sorry, guys. 82. So we have a difference of 12 and a standard deviation of 5.6. And so I see that I'm about 2.14. So you actually scored unusually high. You were 2.14 above the mean. Now let's see, your friend. We could have given her a name, but it's okay. So her z-score, well, let's see. She scored a 91. The mean was 88, and the standard deviation 4%. And so what do we get here? 3/4, so 0.75. She was much closer to the mean. So because your score was farther above the mean, you, even though you got a B and your friend got an A, you scored relatively higher than your friend. Your friend's going to look around the class and have a lot more people that are within or near her grade. You, on the other hand, are not, because like we said, if we had that normality assumption, remember, a z-score more than 2, right? Let's call that 2. Remember how many scores would be in here? Like 95%. So you're in rarefied air up there. So you did much better relative to the class than your friend. And again, we got that by looking at these z-scores. That's because the data then is decontextualized, and essentially, to use a cliche, we are able to compare apples with apples. Here's another one. Number of 911 calls per hour at 5 randomly chosen times are 2, 4, 3, 5, 12. Are any of these values unusual? Well, what we don't have here is a mean or standard deviation. We have to get it from this set of numbers. Now notice it's a sample, so X bar and S. Now to do that, let's head over to Excel. So I'm going to also share, where's my Excel screen here? I'll get it here in a second. Let's see. There it is. Okay. So we're going to share Excel, and I can show you what I do here. One of the ways to do this is you can just kind of come in here and highlight these, and then Control-C to copy them, and then you can go put them in Excel. And one of the things you might notice is that these data values are given as a list, but they are delimited with commas, and they're not all in their own cells. Well, one nice thing is this text to columns feature. So I'm going to hit text to columns, and I'm going to say delimited with, and then I can define comma. And so what it does is it says, okay, wherever there's a comma, I'm going to start a new cell. And so it's going to take this data and turn it into that, which is nice, because now I can say equals average of those. It gives me the average of 5.2. And then also the standard deviation. And again, remember, this is a sample. So we want STDEV period S dot S. And that will give me the standard deviation. So let's call the mean 5.2 and the standard deviation 3.96. So 5.2 and 3.96. Oh, where are we here? Okay. So we've got 5.2 and 3.96. All right, so unusual values. Essentially, I want X plus 2 standard deviations. So 5.2 plus 2.396, which equals, let's see what we get here. 5.2 plus 2 times 3.96, 13.12. And then on the other end, X bar minus 2 standard deviations. And I get which obviously in a physical sense doesn't make a lot of sense. So would any of these be unusual? No, right? We don't have any above 13.12, and you know, this obviously is physically doesn't have a lot of meaning on the low end. So yeah, no unusual values. All right, guys. So that's one application of means and standard deviations. Big takeaways here: empirical rule, and the empirical rule as it's manifested both with the standard normal distribution and the normal distribution. Understanding the use of Z-scores, how they can help us compare, relatively speaking. And then in a lesser extent, Chebyshevs. You're not going to see a whole lot of that, particularly in this course. So that really focusing on, in large part, on the importance of the normal distribution and how that empirical rule operates, and then finding Z-scores. All right, we will talk next about the box and whisker plot and see how that operates. And then we will be done with this section. See you soon.